So we've been simulating this rocket motion in Scratch, and let's take a look at what the flight looks like. We see this kind of parabolic flight, and there's a certain kind of realism to this shape. One of the most realistic things is the timing. So where is the rocket going fastest and where is it going slowest? It looks to me like it's slowing down up here, and there's actually a way we can see that. There's a reason we color-coded these. I see that I have a longer line segment here in green and in the blue, and then a much shorter line segment here in magenta and orange at the top. So what I can tell, since I know each of these is an equal amount of time, that when the rocket is going further before the color change, the rocket is going faster. So the rocket is slowing down the whole time it goes up, and as it comes back down, it's speeding up again. It's converting kinetic energy into potential energy here as it goes to a higher altitude, and then the conversion happens back in the reverse order on the way back. So that has a certain kind of realism to it, but we know when we look at actual launches that things are a little bit more complicated than that. Let's take a look at an actual launch. So what we're looking at here is a recent launch, and I think you'll see that the bottle is going to fall a lot more slowly than it would if there weren't some kind of aerodynamic force on it. Let's take a look at that descent. Here is maybe an even more quantitatively dramatic example. What we're going to see up here in the right is we've got a stopwatch, and I'm going to watch that stopwatch and mark when the rocket reaches its highest point and then when it lands. And I think you'll see that there's a big asymmetry in the time it takes to go up and the time it takes to go down. Let's take a look. There's the max height at 1.85 seconds. Here you can see it really cruising down at a much more moderate speed. It took 1.85 seconds to come up, and then almost 6 seconds total flight. So that means that we've got almost 2 seconds going up, but over 4 seconds to come back down. So that's a really asymmetric timing on the flight. Here's another tragic example, and I think you'll be able to see a certain kind of asymmetry in this flight as well. Let's take a look. Viewer discretion is advised. Tragic. So the peak in this flight occurred right about here. Let's take a look at it again. We're launching from way over here, and the peak happens much closer to call-in on the right-hand side. So it covered a lot more distance on the way up than it did on the way down before its untimely demise. Here we're going to take a look at a redo of this simulation where we've added drag. We've got a drag coefficient here that's pretty small. I've got 0.008 for my drag coefficient, and I'm launching at about 45-degree angle. Let's see what happens in this flight. So this is really dramatically different from the parabolic flight we got before, even though we have a pretty small drag coefficient, or at least it looks like it is. So what I have here is a really long line segment to start. We've got some really fast travel at the beginning, and we can see that we're really rapidly losing velocity, and all the time we're losing speed. So this thing looks like just gravity can't even keep up with the amount of air drag that this is subjected to. So we've got a really asymmetric flight, and it's asymmetric both in that it travels a lot further before reaching the apex, before it comes down, and also in that it takes a lot longer to come down than it does to get to the top. So we want to see how we can implement this kind of effect in our code with a drag term. We can start with Newton's second law. It's usually a good place to start in physics, and I'm writing my MA term on the left here because the acceleration is the thing that's the effect, the thing I care about that I want to simulate. So I usually like to put effects on the left and causes on the right, and our causes in physics are the things we call forces. So let's make this a little bit simpler. Since acceleration is the thing I care about, let's divide both sides by m. So I can say acceleration is 1 over m times the net force. And we can make this even a little bit clearer what we mean by acceleration. I know it's how quickly the velocity is changing with respect to something, with respect to time. So it's the change in velocity over the change in time. That's a, and that's equal to 1 over m times the net force. The thing I really care about updating in my code is the velocity, so I want to know how much to change by. That's delta v. so I could multiply both sides by delta t, bringing my delta t over here. And now I have an expression just for my change in velocity. It's 1 over m times the net force, whatever that is, times how much time has gone by. So now we want to focus on what these net forces are. We know they're relatively simple. We have a force we've been simulating all along, the force of gravity, which simply always points down, and I know how big this force is. This force is equal to mg, where m is the mass of the object, and g is a vector pointing downward, and on Earth it's negative 9.8, or we often round it to negative 10. The negative meaning that it points down. Notice there's something nice here with this term. The m's cancel, so I could handle this term all by itself with just an acceleration equal to g pointing downward. But now we've got this more complicated term, the force of drag, and we want to figure out how big is it and what direction does it point. A lot of the complication is that it doesn't always point in the same direction, but some of the complication is this term always changes in size. So let's see how that is calculated. We've been using a model where we have drag. I know this looks really ugly. It's proportional to the square of the speed. This is a constant of proportionality that depends on the shape of your rocket and the density of the air that it's moving in. We're just going to summarize both of those effects for now in a drag coefficient. Drag is the adjective, coefficient is the noun, so we've got a c sub d. Now, it's proportional to the speed squared. Why is that? Well, if I double the speed of the rocket, I know that I'm doubling the amount of air that I collide with per time, so that's one reason that I'm going to have more drag. But I'm also doubling the relative speed of the air particles hitting the rocket, so they're having twice the effect in changing the momentum of the rocket. So we're having an effect both from hitting more air molecules and from hitting them harder. So that's two effects, and we get a proportionality to v squared. This is a very common model for drag. We also have a direction. This thing looks ugly, but what I see is that I have a vector on top, the v vector, the velocity vector, so that tells me the direction, the velocity of the rocket is moving through the air. And here I have divided by the magnitude of that vector. So if I take a vector, suppose its length is 5, and then I divide by 5, what's the length of the new vector? 5 over 5. Well, it's just a vector of length 1, but what direction does it point? It points in the direction of v. So this is just a handy way to figure out the direction this vector needs to point, and I see it points in the direction of v. Nope, opposite the direction of v. And this part here in the parentheses just represents the direction. This part over here represents the magnitude. So often when we have a vector like this whose length is 1, we summarize it by putting a hat on the vector. Hat means unit vector or a vector of length 1. And you might notice, let's go back, I took this minus sign and moved it over to here because I know it's just telling me the direction is opposite the direction of v. So let's see how we can put these two terms in the code and why we use functions to do this. Well, I see there are just two things I need to do. I need to update the velocity based on gravity, and now I need to update the velocity based on the drag. So suppose I'm looking at my code. I have a really simple loop. Repeat while the height of the rocket is greater than the height that I started. So what do I need to do as long as that's happening? I need to use my step forward Euler function, and I need to have an apply linear drag function. And maybe this drag function should be inside this forward Euler function so that I'm simulating the effect of these both being inside the parentheses here. But I could just distribute this delta t and do the two terms separately. So what does a step forward Euler function do? We've been looking at that for a while. I know it updates my position, so my x position is changed by the rate of change vx times dt. Similarly, y is changed by vy times dt. And we also update vy and vx. Vy is updated by the rate of change of y, which is g, and vx is updated by, oh, it's not updated at all, so I don't really even need this block, but I put it here for symmetry reasons because it looks nice. This shows me that there's no gravity acting in the x direction. So that's pretty simple. So this function takes an input, xy, position, and velocity, vx, vy, and it updates those values to a new position and velocity a short time dt later. If we look at that schematically, in goes x, y, vx, and vy. We turn a crank, we apply these operations, and out we get new values for xy and new values for vx, vy. What should a drag function do? Let's look at it in the same way. Well, we know drag is a force, and force changes velocity, so we need to change the velocity. Velocity has two properties. It has magnitude, how big it is, and it has direction, which we could characterize with an angle or by looking at the components. So this function maybe should be applied inside the step-forward Euler function. We can think about that while we're designing our code. But this function by itself, I need an input Vx, Vy, apply the drag, and that gives me an output Vx, Vy, updated after that force is applied. What happens inside the function? Well, I know I need to figure out how big is v squared, because I know the drag force is proportional to the square of the speed. There's one other thing I need to know. What direction does this force apply? Drag force is in the direction opposite the velocity vector, so I need a way to calculate that as well. So here's my rocket. It's moving through space. It's moving in a direction v. Well, the convenient thing about vectors is that they can always be broken into components in a coordinate system. So this has velocity vx horizontally and vy vertically. How, if I know vy and vx, could I possibly find v? I'm sure that everyone can see what I could do with this purple vector here to make one of my favorite shapes. Now I've got an adjacent side and an opposite side relative to this angle here. So I could maybe use some trigonometry to find the direction. But how do I find the magnitude v? I can use the result found by an ancient cult, the Pythagorean theorem, to find v. Relatively simple. And then this angle theta here, what do? Well, I see the opposite and the adjacent. So I'm thinking of a certain function to represent that theta. I know the tangent of theta is vy over vx. If only there were a way to undo this tangent function, I could get theta by itself. So here's our rocket. I know the drag force here in maroon is pointing opposite the velocity vector. I'm not sure how big it is. That's determined by CD and v squared. But I want to know the direction. So this angle is the same as this angle that we just calculated. How could we undo that? So I've got an input, I apply the drag, and an output. I need to find the square of the speed, and I need to find the direction. So calculating the square of the speed, calculating the angle of the vector. Let's pop this in. The speed squared, remember the ancient cult theorem, that's how I find v squared. And I need to calculate the angle vector. So I need some kind of undo tangent function. What could that be? I'm going to set my theta equal to the inverse tangent or arctangent of something involving vy and vx. So I'm going to set the square of the speed, the angle that I care about, and then change vx by cd times speed squared. That's our model for speed. And then here's how I get the direction. I take the cosine of theta for the x component and the sine of theta for the y component. I multiply by dt because how much my velocity changes depends on the rate of change, which is all this stuff, and how much time goes by. Don't forget to divide by m because f equals ma, and we moved our m to the other side, remember? We divided both sides by m. So that's what the functions look like, and I'd like you to see, can you add this function to your code so that you can get this more realistic motion?